This is video 2 for the DC motor unit. So another important thing we need to talk about with DC motors is voltage. The four characteristics, stall, torque, stall current, free speed, and free current, those four values, whatever those numbers are, will change with the amount of voltage that's applied to the DC motor. So voltage itself is energy per unit charge. So the higher the voltage, the more energy each charge has. That allows the charges to move faster, increasing the current. Power, which is measured in watts, is a way of calculating how much the energy changes. So power would calculate how much of the electrical energy becomes mechanical energy through the DC motor. The power itself will also change with the voltage. Power, which normally equals work over time, well, for electricity, power can equal current times voltage. So notice that if the current is a constant, the more voltage means more power, which means it's faster for the motor to do work. So if the load is held constant, so if you just put a wheel in the motor and turn it on, by increasing the voltage, you make it spin faster. On your joystick, you'll have the two thumb joysticks on your controller. That's what they do. They increase the voltage. It tells the microcomputer how much voltage to send to the motors. So the four main characteristics, they're related to the voltage applied to the motor. So what you would say is the free speed is 50 RPMs at 6 volts, but 100 RPMs at 12 volts. So the free speed can change depending upon the voltage applied to the motor. This relationship between voltage and characteristic is linear. So we can use proportions if we want to make some sort of calculations. So looking at this graph here, I've got motor speed versus torque. And for all of these, notice that as the load increases, the motor speed decreases. And again, that should make sense. So here's the difference. Each one of these lines represents a different voltage. So here, the red line, we have 18 volts. So at 18 volts, the free speed is 300 RPMs and the stall torque is 30 Newton meters. If I decrease the voltage to 12 volts, now the free speed is only 200 RPMs and the stall torque is 20 Newton meters. We haven't changed the motor. The motor's still the same. What we've changed is the voltage we apply to the motor. At 6 volts, the free speed is 100 RPMs and the stall torque is 10 Newton meters. So by changing the voltage, we change those four characteristics. So as an example, we have a motor whose free speed is 50 RPMs at 6 volts. What would the free speed be at 8 volts? And to answer this, we can just set up a simple proportion. So we have 50 RPMs at 6 volts, and we want to find out the new free speed at 8 volts. So at this point, it's two fractions equaling each other. You just have to cross multiply. So when I cross multiply, I find that the new free speed would be 66.66 RPMs. And again, we just cross multiply. And solve it using proportions. So let's take a look at what our own DC motors can handle. So, the VEX 2-wire 393 motor. It has a free speed of 100 RPMs, a stall torque of 1.67 newton meters, the stall current is 4.8 amps, and the free current is 0.37 amps. So, what we want to calculate then is how much load can this motor handle. So in this example, we have a robotic arm. And we have our motor, it's at 7.2 volts, so those four characteristics, the 100, 1.67, 4.8, 0.37, those are all at 7.2 volts. So what I want to calculate is how much can this thing lift? The arm is 0.25 meters, and if we think about it, when the arm is all the way down here with that ball, it's going to take very, very little torque to move it. But as it travels up here, it's going to slow down because the torque is going to start increasing. So torque itself equals a force that is perpendicular to a lever arm. So looking at our diagram, the length of this arm is our lever arm, and the weight of this object is our perpendicular force. So what we want to do is we want to solve for that perpendicular force. And we're going to use the stall torque for our torque, because that is the greatest torque that motor can provide. So the force would equal torque divided by lever arm distance. We want to make sure everything's in meters. So we find that it'll pick up 6.7, 6.68 newtons. That is roughly 1.5 pounds. So what this means then is that the motor will slowly lift this weight up until it stops at that location. It's then going to draw a stall current while it holds the weight in place. When an application requires more power than a single motor can handle, as a designer, you basically have three options. First one is to deal with it. You're under limitations. Change your design. Maybe there's something fundamentally flawed with your design. Your second option, switch to a more powerful motor. We don't really have that option available to us. I do have some gearing where we can go between a high-speed and a low-speed version of our DC motors, but it's something we can take a look at. Your third option would be to use more than one motor. So if you choose to use more than one motor, the load applied to them will be balanced between the motors, which is kind of nice. So let's take a look at our charts here then. So a single 393 motor, again it's free speed, and this is all at 7.2 volts. Free speed is 100 RPMs, stall torque's 1.67, stall current 4.8, free current 0.37. And again, I do have a high-speed I have some high-speed gears that we can tear apart the motors and replace the gears inside the motors. It'll bump your free speed up to 160 RPMs, but notice the torque, stall torque, drops quite a bit. It still draws the same currents, however. Now, if I have two motors, notice that the speed does not change. Just because you add more motors does not speed it up. You know, they're limited by how fast they can turn. But look at the stall torque, 3.34 Newton meters. If you do a little bit of math, you'll see that's double 1.67. Now it also draws more current, which should make sense. There's more motors, so it should draw more current. So now it's drawing 9.6 amps for the stall current and 0.74 amps for the free current. So by using more than one motor, you're pulling more amperage out of the battery. But what you're doing is you're doubling your stall torque. For the high-speed variations, you can see how you once again you double your stall torque over there. So let's take a look at this problem right here. It's the same setup as before. We got an R value, or a lever arm distance of 0.25 meters. This time, my perpendicular force I know is 22 newtons. So what I want to calculate is, well, how many 393 motors do I need to accomplish this task? So to do that, let's calculate how much torque is needed. So torque is a perpendicular lever arm times a force, or a force that's perpendicular to a lever arm. So that's going to be 22 newtons multiplied by 0.25 meters. So the torque I need is 5.5 Newton meters. From there, I just take that and divide it by the stall torque of a single 393 motor. And this gives me 3.29. I can't have 0.29 motors. So even if it's 3.001, you still have to round it up. I need to have 4 motors. This concludes our entire unit on DC motors.